going to be solving a problem that came in the academic quiz of further math this weekend. So the question reads, given in, which is that bulky integral for all n greater or equal to 0, prove that 2n in plus 1 is equal to 2n minus 1 in plus 2 to the negative n, and hence evaluate I3. Okay, so basically in this video I'm going to prove Roman 1 and then Roman 2. I'm just going to explain and then you're going to do it. You can post your answer in the comment section. If your answer is correct for Roman 2, I am going to reply, and at the end I am going to post the correct solution to evaluating I3. Okay, so let's get started with this question. First of all, it is from a topic known as further integration. We refer to the topic as reduction formulae. So we are going to see how to approach questions like this. The A part is asking us to show that 2n in plus 1 is equal to 2n minus 1 in plus 2 to the negative n. Now n is greater or equal to 0. So it's going to be very, very nice if we do something with our denominator of the integral, that is this integral. Now we can work with it like this, but when I was solving the equation, I actually saw a technique that we can use and make it to resemble something that is familiar actually. Now there's also one thing, whenever you see negative limits, it's always good to try a way to change it to positive limits. Like here, the limits are from -1 to 0. It's really bizarre, so we can try a way to change the limits and see if there is a possibility for your bounds to be positive, then it's going to be nice. But if there is no possibility, then we proceed like that. Okay, so let me show you guys a trick that I used to solve this problem. Okay, now I identify my denominator as x squared plus 2x plus 1 plus 1. Why? Because I know that x squared plus 2x plus 1 plus 1 is simply a difference, or is simply a perfect square, sorry, because this 2 here can be written as 1 plus 1. So from there I get it as x plus 1 all squared, then plus 1, because x squared plus 2x plus 1 is x plus 1 all squared, and I add this one to it. So from there I can rewrite my integral as what? The integral from -1 to 0 of the x on x plus 1 all squared, then plus 1, all that raised to the power n. It's now looking a bit nice. Now let me try to see if I can change the limits, because I see that what? If I can replace just one quantity with x plus 1, I know that if I differentiate x plus 1, I will get the x. So simply I will do a change of variable. So if I let s to be equal to x plus 1, then I am now changing from the x wall to the s wall. So I will need to look for the x. The x is going to give me the s, which I'm going to substitute back here. But now these my bounds are still in the x wall, so I'm going to take them to the s wall. So I need to change those bounds. X begins from -1 to 0. Now when x is equal to -1, my s becomes -1 plus 1, which is 0. When x is equal to 0, my s is 0 plus 1, which is 1. I am good now because I have positive bounds, so I can proceed. Okay, so it means my in will simply be equal to this integral, the integral from the initial value of s to its final value, which is from 0 to 1. Now in the place of the x, I'm going to replace it with the s, because I have changed from the x to the s wall. Now in the place of x plus 1, I am going to replace it with s, but remember it is all squared, and then plus 1, this plus 1, then all of that raised to the power n. Now it looks something nice. Now I need to prove this relationship. So for me to do anything here, because generally with reduction formulae we use integration by parts. That's what we use generally. But now it depends now on how your proof is being structured. You see, if like here you have 2n in plus 1, so you see in your proof you have a relationship between in plus 1 and in. Now when you come to your integrand, because generally you need a u and a dv when you're doing integration by parts, your u is a function that you can easily differentiate and your dv is a function that you can easily integrate. Now you see in this case, I see that if I differentiate 1 over s squared plus 1, the denominator is going to have n plus 1, and it's a bit, I can, if I work it out, maybe I can get an in plus 1 from there. That's how you begin to build your proof to know what to let to be u and what to let to be dv. So simply, if I use integration by parts in this case, I will let u to be equal to 1 over s squared plus 1. Now when I differentiate it, simply I can write this as s squared plus 1 to the negative n. So differentiating, what I do is that I drop the power, which is negative n, I differentiate the integral, it gives me 2s, and then I take multiplied by the very function to this power minus 1. The power is negative, that's negative n minus 1. So I can rewrite it as what? Negative 2ns. Now since the power is negative n minus 1, I can write it as negative into n plus 1, and then now I bring it down to the denominator, and then I get this. That's basics of differentiation. So I've gotten my du. Now next, my dv now is simply going to be ds. Doing it that way, it means that what? Integral of dv will give me the integral of ds, because I need to find v, that's why I'm integrating dv. From there, I get my v to be equal to s. Now what's the formula of integration by parts? In is equal to uv. Now my limits are from 0 to 1 minus the integral from 0 to 1 of v du. Alright, so from there I simply replace the values. First we begin with uv. Our u is 1 over s squared plus 1 to the n, and our v is s. So simply we get this. Now my boundary, my bounds are 0 and 1. Now next we get minus the integral from 0 to 1 of v du. But now du, which is this, has a negative, so it annuls with this to become a positive. Now our s is going to multiply with s here to give us s squared, and then we can keep this 2n outside because it's a constant. We get this. It's very important for us to put a ds here, so let's take note. We need to add that ds, because without the ds it makes everything wrong, because we're integrating with respect to s. So it was just an error that I made when I was typing the solution. Probably the error is going to follow along, but anyways, let's just proceed. So from here we can try to fit our upper limit, right? When we fit 1, we have 1 divided by 1 squared plus 1, which is 2, then to the n, 1 over 2 to the n. When we fit 0, we have 0 divided by 1 to the n, which is 0. So simply this gives us 1 over 2 to the n. Now here I'm going to rewrite this. Okay, so I included a ds here, so that's good. Here I'm going to write my 2n remains intact, but now s squared plus 1 to the n plus 1 is the same as s squared plus 1 times s squared plus 1 to the n. Now I have an s squared here. I brought this out because I want to separate what is with n and what is not with n. Now let's try to simplify this guy here to see what we get. So s squared plus 1 divided by s squared divided by s squared plus 1. We can use long division, but we can also do something that is very basic. We try to make the denominator to look like, we try to make the numerator to look like the denominator, but at the same time the numerator. It's a bit confusing, but this is what we are trying to do. We are trying to make s squared plus 1 to look like, we are trying to make s squared to look like x s squared plus 1, but still s squared at the end. So simply what we'll do is that we add and subtract 1 to s squared. Adding and subtracting 1 remains keeps that intact, because 1 minus 1 is 0. Now we try to group s squared plus 1 to itself, and then negative 1 to itself. They have the same denominator, so we just do the division, and we get s squared plus 1 divided by s squared plus 1 minus 1 divided by s squared plus 1. Now this is going to give us 1, and then this remains intact. So I'm going to replace it here. So it means that my in 1 over 2 to the n is 2 to the negative n. Now plus 2n times s squared divided by s squared plus 1 is 1 minus 1 on s squared plus 1, then times this quantity. Now we have 2 to the negative n. We now try to distribute this, or we distribute this here and here. Doing the first time, we get 2n times, when we do this times 1, it remains. Now doing the second time, remember you have a 2n here, then this is a negative sign, then this multiplies with this. They have a common denominator, so you just add the powers. So you get negative 2n on the integral from 0 to 1 of this quantity. Now originally we were being told that this is in, that's it, it is in. So definitely this is going to be in plus 1, because simply the power of s squared plus 1 is n plus 1. So this is in plus 1. So we can write this as in is equal to 2 to the negative n, plus you have 2n times in, then minus 2n times in plus 1. From there we are good. We can take this quantity to this side, and then in to this side, and then we get the proof automatically. So that's basically how you use reduction formulae to prove relationships like this.